Polyprotic acids and bases are compounds that can either donate more than one proton or accept more than one proton, and these are presented very nicely in section 15.8 of the Chang textbook. Carbonic acid is a good example of a diprotic acid. It is a weak acid that undergoes a weak acid dissociation in water to produce a proton in aqueous solution and a conjugate base. It is the conjugate base then from step 1 that can go on in a subsequent step to release another proton in an acid equilibrium. In all cases, the first proton given off has a much larger equilibrium constant. The equilibrium constants for the first proton, Ka1, is products over reactants, and then the second proton also has its own equilibrium constant labeled Ka2, and Ka1 is always significantly larger than Ka2, and for carbonic acid, Ka1 is 4 times 10 to the minus 7, and 100,000 times smaller is Ka2, 4 times 10 to the minus 11. So there's always a very large difference between how easily the first proton is released in water to how the second proton is released from the subsequent conjugate base. Let's examine another diprotic acid. Malonic acid is 2 carboxylic acids, and the first proton comes off when malonic acid is placed in water, and then it is the conjugate base from the first step that can release the second proton in water. And again, Ka1 is 1 times 10 to the minus 3, and Ka2 is about 2,000 times smaller than Ka1. So what we want to look at is when malonic acid, just a white crystalline powder, is placed into water. What species are present? I want to draw the species present in solution, and it would be very difficult to put the full chemical structure for malonic acid, and so we will show the weak diprotic acid is H2A, so 2 protons would then dissociate into H+, and we can label the conjugate base HA-. HA-, of course, is the reactant in the second step, and then the final conjugate base, the dianion malonate, we can represent as A2-. So we are going to place into solution, into an aqueous solution, some malonic acid. This is a weak acid, and so hardly dissociates at all. At concentrations of 1 molar, we would expect about 95% of the weak acid to remain in solution, and only 5% of the acid to dissociate into HA and H+. Now, in calculating the acidity of this solution, we're going to assume that all the proton concentration is entirely governed by the first dissociation step. The idea is the second step is a small equilibrium constant, and there is very little HA- in solution to begin with. So all protons in solution come from the first dissociation step. Another observation that if the first dissociation step is the dominant step, then the HA- concentration and the H+ concentration will be equal in this solution. There's a consequence to this equality that we'll explore. So when the HA- and the H+ are the same, this has an interesting impact on the dianion in solution. So A2- we know is going to be present in very small quantities, but quantities that are calculable. So A2- is only produced in the second equilibrium. So Ka2 describes the equilibrium that produces A2-, and it's products over reactants. And if we examine the relationship in the solution, that the HA minus and H plus are the same, in this expression those two would cancel, and the A2 minus concentration will be very close to Ka2 for the second step. And so in solution we would expect 2 times 10 to the minus 6 molar A2 minus present, and present in very small quantities. Let's examine the titration of a diprotic acid. So a diprotic acid, we really will think of this as 2 separate titrations. A strong base titrating a weak diprotic acid will undergo first titration of the first proton and have an equivalence point, and then after the first equivalence point, the hydroxide now starts titrating the second proton, and we see then a second titration equivalence point at the inflection. And importantly, if it takes 25 milliliters of base to neutralize all of the H2A in solution, it will take another 25 milliliters to titrate all the HA minus in solution. So on the x-axis, the inflection points occur 25 milliliters in this case of strong base, and then another 25 milliliters up to 50 will be required to reach the second endpoint. Now, as we have done for all of our titrations, drawing a cartoon image of the abundant species in solution is useful to thinking about the process that is occurring during this titration. So we will start thinking about the beaker with the acid at 0 milliliters of NaOH, and this is a weak acid, so it's not dissociating very much on its own. Its dissociation doesn't take place until hydroxide begins to neutralize the weak acid. So we will move to where that has taken place substantially. The first reaction is the only reaction occurring, and we'll draw the picture at 18 milliliters of sodium hydroxide. At this point, we are well into neutralizing much of the H2A in solution and producing HA minus. So we still haven't neutralized all of the diprotic acid, but we're now building up the conjugate base of the first step. It is not until the first equivalence point, and we'll draw that picture, where we have completely neutralized all of the original H2A, and at the 25 milliliter mark where the first inflection point occurs, we have now neutralized all the H2A, and the compound exclusively present is HA minus. We haven't begun to neutralize any of the HA minus, and that is all done in the second titration reaction. Into the second titration, we will examine the system at 31 milliliters of sodium hydroxide added, and the second reaction has begun to occur. We're neutralizing the HA minus with the strong base hydroxide, and at this point we've only neutralized a little bit of HA minus, and the amount that we have neutralized has been converted into A2 minus. We'll go all the way to the second equivalence point. We have completely neutralized all of the HA minus in solution, and at 50 milliliters we only have dianion conjugate base A2 minus. We'll look at one final spot past the second equivalence point. This is at 56 milliliters, and now neutralization of hydroxide has ceased after the second equivalence point. There is no weak acid to neutralize the hydroxide, so what happens is the A2 minus remains in solution as a weak base, and hydroxide is now not being neutralized. So after the 50 mil mark at 56 milliliters, there has now been 6 milliliters of unneutralized hydroxide added to the solution. An extremely important diprotic system are amino acids. This is the amino acid glycine. Amino acids are capable of producing 2 protons in chemical reactions. The neutral form of an amino acid is monoprotic. It's not until the pH is reduced significantly that a second proton is added to the amino acid and in fact makes this a cation. But as we know, cations are good acids, and this protonated form of the amino acid is what we observe in systems at low pH. The completely dissociated form of the amino acid is in its anionic form. The titration curve for an amino acid, which you're likely to see in biochemistry, is a two endpoint titration. First endpoint and then second endpoint at high pH. And so again, thinking about the species present in solution, at low pH, the diprotic cation is the form of the amino acid, and then as strong base is added, at the first equivalence point, the neutral form of amino acids are observed, and then finally it's not till very high pH that we can pull off this last proton and the anionic form of the amino acid is observed. Now, the Kas of amino acids, of course, can be found from the titration curve, and this is a popular biochemistry experiment. At halfway to the first equivalence point, the diprotic form of the amino acid is the exact same concentration as the neutral form of the amino acid, and so at this pH, that is equal to pKa1. So the pH is 3 at halfway to the equivalence point, and the Ka for the amino acid being titrated would be 1 times 10 to the minus 3. The halfway to the equivalence point for this second proton removal is occurring at pH 10, and so the Ka will be 10 to the minus 10 when Ha and A minus are equivalent concentrations. The last example of a double titration curve is a dibasic situation where we place sodium carbonate into solution. Sodium is of course a spectator ion, so this is a solution that is dibasic. Carbonate can neutralize 2 protons in solution, and the first neutralization step would be carbonate turning into bicarbonate, and that occurs for the first 25 milliliters of this titration until the solution is entirely bicarbonate, and then bicarbonate can continue to neutralize strong acid by converting into carbonic acid. Once again, if it takes 25 milliliters to neutralize carbonate, it will take another 25 milliliters of strong acid to neutralize the bicarbonate.